Okay, and now here are the apparatus we're going to use for this experiment. Take a close look. It might be hard to see in this video. Heart of the system is this physical pendulum. This is a disc, and at the end, and on one edge of the disc, there's a weight. Okay, I put a little red flag on the weight so you can see it clearly. If I displace the disc, then gravity acting on the weight will provide a torque that pulls this back to the initial position. Now, the system has is additionally attached to these springs here. These are probably hard to see, but there's a spring on either side which is attached to the disc through a pulley on the back. One side of the string is attached to a fixed point here, and the other side is attached to a drive unit here. There's a motor, and when it turns, it will pull on the string, of course, displace the string, and that will also provide a torque on the system. So we can drive the system by using a motor. Here, I'll turn it on for a second so you can see what I'm talking about. There we go. You get the idea. Finally, the system is connected to Logger Pro using two sensors. There's a rotary motion sensor here, just like in the coupled oscillator lab. And then there's one more thing. There's a photo gate, which is monitoring the rotation of the motor. Each time the motor goes through one cycle, it triggers the photo gate. And that's going to let you eventually figure out the period of the rotary motion, and thus know what the phase angle of the drive is when you do your analysis, which will be useful when we make what are called Poincaré sections later. Here, let's take a look at the way the data is going to be recorded in Logger Pro. There are several graphs we're going to make. The first one is going to be a graph of angle versus time for the pendulum. The second one is going to be the Fourier transform of that information. So it will show you the angular displacement as a function of frequency. If we had periodic motion, we'd expect a peak at some well-defined frequency. The third graph will show the angular velocity as a function of the angle. That is, it's going to make a phase plot. And you'll see how useful that is when we start to do our experiment. Sound good? Okay, let's go ahead and do our first experiment so you can see how everything works. In the first experiment, we're going to look at the undriven motion of this system. So we'll just displace the oscillator by, let's say, 50 or 60 degrees. We'll release it, and then we'll start the data collection. Off we go. There we are. While this is running, I'm just going to readjust the position on the graph. Just about done. Okay, now we're done. Can you see what we got? Here we saw an oscillating wave that decays. So we have a damped oscillatory motion. No surprise. When we look at the Fourier transform of that, we get a peak. And the peak is at a well-defined frequency, about 1 hertz. And it has some width. And the width of the peak should be telling us something about the damping rate that we see in the upper plot. These are connected. But the most interesting, perhaps, is the phase plot. Can you see what the phase plot looks like? It's a little hard to see. Let me bring the monitor, camera closer. So perhaps you can see that this is a spiral. The motion essentially is circular, but due to damping, as energy leaks out, the amplitude of motion and the velocity of motion are slowly decreasing over time, until finally the system ends up at the origin, where 0 velocity and 0 displacement. Okay? Okay, let's stop there.